A lot of the expense and difficulty of doing an experiment is setting up the input variables. And it's a great economy if you can have more than one output variable of interest measured against the same set of input variables. So here's a sample data set. This is a hypothetical example out of building seat belts. And the question is, you've got two output variables. One's engagement distance, and that's how much seat belt the mechanism pays out before it locks up in a wreck. And the other is pawl insertion. The way that you lock it up is there's a little gear mechanism, and you just jam a pawl in between the teeth, and there's a maximum spec for the amount of webbing that you can pay out, and there's a minimum spec for how far that pawl gets into the gear teeth within a few milliseconds. And here are four input variables that might influence that. And this is the pawl tooth gap, and the pivot lever height, surface finish, and I've forgotten what RLPC stands for. But I can just simply designate two different, or more than two, different output variables, and I can then run both of them simultaneously against the same set of input variables. Now, let me add an X here and one more here, and then I'll hit calculate. And here are my results. Apparently, my model for pawl insertion is pretty good. You can see the needles and sliders, and I'm looking at PI here. Now, to switch over to ED, I then just use this drop-down box, and everything changes across here, except in the optimizer, I will simultaneously get both of my output variables. So that's very nice. Having gone to the trouble of building the model, I can then make any adjustments that I want here and watch simultaneously what it does to my two output variables.